Hey folks, welcome to this episode on methods of measuring rates of reaction. So when we're looking at rates of reaction, we're looking at either the production or the consumption, or therefore the change in production or change in consumption of a reactant or product over a set amount of period of time. And so any method that allows us to figure out the initial and the final values will allow us to figure out a rate. And so we have a number of different ways available to us to actually discover what this change is, but the method that we choose to use really depends on the substances that are involved. So for example, if we have a reaction that doesn't produce a gas, then we can't really look at the rate of production of a gas over time. It just doesn't work. We have no gas to measure. We can't do it. So we really have to choose a method that works best for us, and it really doesn't matter what method. The rates that you get should really be the same. So let's take, for example, this reaction at the bottom here. We have calcium carbonate reacting with hydrochloric acid to produce calcium chloride and carbonic acid. Remember that carbonic acid breaks apart into water and CO2, and that's what we're going to have over here. So let's take a look at how we can actually measure this reaction. So the first thing you notice is that because carbonic acid breaks down, we have the production of CO2. So we can look at the rate of production of this CO2 over time. And we can do that using a gas syringe, for example. Now, this gas syringe has little graduations on here, and you can see how much it's being plunged over a certain amount of time. Now, we wouldn't be able to get a curve like that. We'd only be able to see the initial minus the final over the change in temperature, over the change in time, but we wouldn't be able to get this kind of slope from this type of measuring. We could get a rate, but we wouldn't be able to get all these individual points over here, these instantaneous rates. However, if we had something like one of these systems here, where you have a gas sensor that senses the volume of gas, the pressure of gas, and you look at the volume, you can graph this on your little module or through the computer and get a nice little slope like that. Either way, what both of these systems are looking at is they're looking at the production of CO2 gas over a certain amount of time. So the change in volume over time. Now, once again, here we have this mass of CaCO3 and HCl. We put this into an Erlenmeyer flask, and if we put a little piece of cotton wool over here, we can figure out what the change in mass is. So we can put this on the scale and look at what the original mass is, if we add our two reactants, we know what the mass of both of our reactants are, and we can see how the mass changes over time. Now, again, why would this mass change? Well, think about it. Here we have a solid, we have a liquid. The law of conservation of mass means that the mass of this should be the same as this mass over here. But what happens is that we're going to have a decrease in mass over time. Why does this take place? Well, it gives you a little hint right over here. Cotton wool allows for gas to escape, but no other matter, so liquid and solids. The reason we put cotton wool, just in case something bubbles up or whatnot or spills, it will still be absorbed here and counted as the mass in total. However, the only thing that can escape is the gas here. And so what we're doing is that the change in mass that we see is due to the loss of, in this case, CO2. The CO2 is escaping from over here, and therefore we're losing the mass in our total system over there. So again, we can look at the change in mass over time. Now, if we have a reaction that changes color, we can use a spectrophotometer, which measures the amount of light of a specific wavelength that's absorbed by this compound, and plot that. In this case here, when we look at this reaction over here, we can see that we can look at our concentrations over time. We have 1 mole per liter, 0.49, 0.24, 0.11, 0.05, and as our concentration decreases, the saturation of the color that's created at those concentration also decreases. So we could take a sampling of this, put it in our little cuvette, and put it into our spectrophotometer, and figure out how much of a certain wavelength is being absorbed. That absorbance over time will give us a rate. We can also look at pH. So using a pH probe, we can look at the change in concentration of H3O, which gives us a pH over time. So again, for our rate here, the rate would be the change in the pH over the change in time. So you can see that we have a lot of different methods available to us. It just depends on what the reaction is and what's being produced. For example, if we have a colorless solution that produces another colorless solution, we wouldn't be able to use a spectrophotometer or the color. We'd have to use something else. But hopefully it evolves a gas. If we evolves a gas, we can look at volume, we can look at pressure, we can also look at change in mass. So there's a bunch of different methods, and they should yield the same rate regardless of which method you choose. Okay, so let's return to this equation here, this reaction, calcium carbonate reacting with hydrochloric acid to produce calcium chloride, water, and CO2 gas. Now, an individual that was investigating this performed this reaction in an Erlenmeyer flask. They filled it up with a little bit of cotton over here and decided to do two different types of measurements. You can see that there's some data over here on mass of the solution. So they've obviously put it onto some kind of scale. Once they did this, they tared it, and they saw what the change was, so they tared it to 0, and they saw that that became a negative mass, which means that this solution in here has lost mass. The way that that happened was, again, because it produced CO2, the CO2 was able to escape, and CO2 obviously has mass, so as mass escaped from this solution, the overall mass of this decreased. Now, the other way that they did this is they hooked this up to a sensor to see how much CO2 in terms of volume of CO2 was produced. So not only can we find a rate from the change in mass, we can also find rate from the production of CO2 or the volume of production. Now this is interesting because this allows us to compare these two methods. They technically should give us the same results in terms of rate. In this case, change of volume over time and change of mass over time. And so this will give us an opportunity to see if that assumption is in fact correct. Now, we're going to have to do a change in volume of gas and a change in mass. So we're good with Kelvin, 2.1 Kelvin, 102.1 kilopascals. Milliliters is something that we don't really work with in terms of volume. So let's turn this into liters. That's going to be 0.0253 liters. Milligrams as well, we don't really work with milligrams, so if we divide it by 1,000, we get 0.047 grams. And then our time is 1 minute, so if we multiply that by 60, we get 300 seconds. Okay, so let's take a look at this. Let's see if we can figure out what our rate is in terms of the change of volume of gas and what our rate is in terms of change in mass. So again, here are our pieces of data. For this one, from volume data, we're not going to really need to use this volume over here. We will need to use this. Again, that's 0.0253 liters. So the first thing that we need to do is, well, what do we have here? We have temperature, we have pressure, we have volume, time. What can we do with this? Well, T, P, and V. Reminds me of an equation called PV is equal to nRT. We could use this equation to figure out how many moles we have, so that change in moles. Once we figure out the change in moles, we can put it over time and figure out our rate. So what we're going to have to do is we're going to have to solve for n, so rearrange this. N is equal to PV over RT. Now once again, we don't remember R, we don't have R given to us, but it is a gas constant, so we will be able to find that out. So let's plug in our values. Our pressure is 102.1 kilopascals multiplied by volume, which is in this case 0.0253 liters, and that's divided by 8.314, and that's liters kPa over mole Kelvin. Okay, and then our T is 291 Kelvin. Now remember, for gas calculations, we must have our temperature in K. Now if you're using atmospheres, this number will be a little bit different, as will this one over here. So if we do this all out, what we get is 1.0677 times 10 to the negative 3 mole. Okay, so this was the change in terms of moles. Now to find out our rate, okay, it's the change in volume, or in this case the change in mole, over the change in time. So we have our moles. We have 1.0677 times 10 to the negative 3 mole, and that's going to be over 5 minutes, or the equivalent of 300 seconds. So if we do this out here, what we're going to see is we get 3.559 times 10 to the negative 6. That's mole per second. If we go into significant figures, we should have 3.56 times 10 to the negative 6 mole per second. So that is our rate in terms of the production of CO2 gas per unit time. So 3.56 times 10 to the 6 mole per second. Now let's look at the mass data. In terms of mass, we're not going to be looking at the volume of CO2 produced, so we can cross that out. Once again, in this case, this value over here, the 47.0 milligrams, that's going to be 0.047 grams. That's minus for our solution. But what we want to look at here is this is minus. That means the solution has decreased in mass. But what we want to try to find out is where did that mass go? And we spoke about this earlier, that this mass was the mass of CO2 that left the solution. So this mass, based on the law of conservation of mass, is equal to the mass of the CO2 lost. If a solution is 0.047 grams lighter, well, that means that based on the law of conservation of mass, the mass that was lost was 0.047 grams of CO2. So now we can use this to figure out our rate here. So once we have our moles, our grams, how do we get it into moles? Again, we want to go into delta N, or change in moles, over our change in time. How can we go from grams into moles? You guessed it, divide by the molar mass. So 0.047 grams divided by the mass of CO2, which is 44.01 grams per mole. Let's divide it here. What we get is 0.0010679 mole. So that's how many moles were our change. Now what we want to do is we're going to take this value and divide it by our seconds. So in this case we had 300 seconds, and our rate is going to be 3.559 times 10 to the negative 6 mole per second. Again, to significant figures, we have 3.56 times 10 to the negative 6 mole per second. This is our rate that we got from mass, which is very similar. 3.56 times 10 to the negative 6 mole per second was the rate that we got from the volume of CO2. So regardless, what this shows us is that regardless of the method you choose, you should get the same rate either which way you do it. Thanks very much for watching. See you guys next time.